Good afternoon, ladies and gentlemen. Today's class recording has started.
I was gonna say it.
Does everybody understand? Does everybody understand the class recording has started?
Yes.
Good. All right. Yesterday, we finished up our discussion of friction, and friction, obviously being a force, falls into this unit. But if we talk about reviewing how friction sort of fits into this picture, right? First type of friction we talked about was what? Static friction, right? Static friction affects what kind of objects?
Motionless.
Motionless. Good. I like that. Okay. So, first, and we kind of talked about this yesterday, is there static friction on this stationary book?
No.
No. Friction needs to oppose something, right? Static friction doesn't show up unless there's something for it to work against. So static friction will only show up when I do what to this book? Apply a force. And what doesn't happen? It doesn't move, right? So if I push, then static friction shows up, okay? If there's no motion. If there's no motion, what is the net force acting on the book? Zero. And the acceleration then is also zero. So that basically falls under which of Newton's laws?
First.
I'd say it's more of a first law thing, right? Okay. First is zero acceleration, right? Things at rest stay at rest. Things in motion stay in motion unless they're acted on by
External force.
a
Outside.
net external force, right? Where we have an unbalance of those forces or an imbalance of those forces. Okay, good there? All right. The other type of friction we talked about was kinetic or sliding friction. That affects what kind of objects? Moving objects, right? Motion objects, right? And it will affect those moving objects in which direction? The opposite of whenever they're moving. So static friction works against a force, where kinetic friction works against a motion, right? If we have an unbalanced kinetic friction force, what will happen to our object? Wow. I haven't seen that happen, but it will do what? It will accelerate. Specifically, what kind of acceleration? If the friction force is acting against the motion, if it's pushing on it in the opposite direction of the way that it's moving, it'll slow it down, right? So we would have what kind of acceleration then? Negative acceleration, right? What has to be true in order for kinetic friction force to be acting on the object? Has to be in motion, right? So it slides, kinetic friction slows it down and stops it. Is there kinetic friction on that book now? No. If there was, what would start happening?
Start moving.
Start moving back the other direction, and that doesn't happen, right? So friction forces, the unbalanced kinetic friction force that slows the book down, that would be an example of which of Newton's second law, right? So that would be an example of Newton's second law, right? Where we have acceleration occurring. And then we would talk about, okay, how much force, how big is the mass, how much acceleration does it have, okay? Good as far as reviewing goes? Okay. The packet that I gave you on Monday has 4 sheets in it. We did one of the sheets that was on the very, very back of the packet. We're actually going to do the sheet together. That is page 3 of the packet that looks like this, that has a guy skydiving out of a helicopter. Okay? Not yet. We'll get there. But yeah, we're going to do this one first. So. Actually, you could grab one of the stools too. That would work. All right. So before we get started, just to make this problem a little bit more personal.
His name's Elton.
Nope. His name is Bronco.
Oh, that's a horrible name. He doesn't
No, look at him. He looks like a Bronco, doesn't he? Like he looks like a guy wearing pajamas. That's what he kind of looks like. All right, so something we're going to need a little bit later on to help us. Bronco's mass is 100 kilograms. Okay, Bronco's mass is 100 kilograms. We're going to need that a little bit later on. So let's talk about this situation right here. Okay, the very first picture that shows up. Okay, our discussion over the next couple days will center on things falling. We've already talked about that, but we made one big assumption about things falling in the previous section when we were talking about acceleration, the acceleration of gravity. Right? What did we assume about our falling objects in the last unit? They weren't affected by air resistance, and therefore they had a what? Acceleration. They had a constant acceleration, and that constant acceleration was what? 9.81 meters per second, or close to 10. Okay? All right, but that's not real life. That's not what happens when things fall through the air. So let's try and take our model now and make it a little bit more like what real life is like. Okay, air resistance. Air resistance is a result of things moving through the air. And as those things move through the air, what do? They move. Why do they slow down? Something is pushing on them. What pushes on them? The air itself, right? As things move through the atmosphere, they run into air molecules, right? 3 states of matter: solid, liquid, gas. Gas is in air, right? We'll get to that later on, right? But even though we can't necessarily see it, it's still there. So as we move through that air, we run into things, and that applies a force in the opposite direction. That's why it's air resistance, okay? But in order to have air resistance, you have to be doing what? Moving, right? I can have air resistance if I'm moving, right? But you have to be moving for that to happen. This is the very beginning of Bronco's skydive, okay? He has just stepped off the leg or the landing gear of the, what do they call those things in the bottom? No, the bottom of the helicopter. The skid, is that what they call it? The skid of the helicopter? Like the, whatever. He just steps off the landing gear of the helicopter, okay? Like we discussed in the last unit, at that very instant where I let the object go, what is it doing? Yes. What is it doing at the very instant that I let it go, though? There's no what? Yes. What tells us about what's happening now? Aha. It's instantaneous velocity is what? 0. Now, just because its velocity is 0, does that mean that its acceleration is 0? Could be, but not necessarily. We're good. Skids. Okay. All right. Thank you. Thank you. Thank you for checking up on that. So. All right. So, at that moment, he's not moving, but he is accelerating. Because what's going to happen immediately after he's not moving? He's going to start moving, right? And that's a change, right? So we can have 0 velocity, but non-zero acceleration. And that's what's going on here. But for our purposes, right, let's talk about how he can be accelerating even if he's not moving. All right. In order to analyze what's going on in a situation, a lot of times we draw ourselves a free body diagram. A free body diagram is a picture that shows us what? Forces, right? Here we have one arrow. It's pointing downward. It's labeled W. What is it going to stand for? Weight. we'll find out a little bit later on today or maybe tomorrow that weight is another way to describe the force of gravity. Okay? Notice that there is a letter R, but it's labeled as 0. In this case, what do you think R is going to stand for? Resistance, right? Air resistance. But why is it 0 right now? It's just left. Air resistance depends on what? Moving. Is he moving yet? No. All right? So, we have forces. We have a free body diagram that helps us analyze those forces. Now we take what the free body diagram tells us and mathematically analyze it using this equation. What does that summarize for us? Net force is equal to mass times acceleration. What concept is that? Newton's second law, right? It tells us about acceleration. A lot of times, and we've done this several times as well, we've rearranged this equation just by dividing both sides by m. So it looks like this. So we can calculate what the acceleration of that object would be in that situation. Okay? The top of this fraction is what? Net force. What does that mean? The total forces acting on an object, right? Mathematically, how do we handle or how do we find the total force? When we have the net force or the sigma in front of something, what do we do mathematically? We add them, all right? So in this case here, we can replace the top of this fraction with W plus R. Okay? That's the addition of the two forces that are acting on that object. Okay? Save your question just for a second. I know some of you might have a question if you look at the sheet, right? It's a little different than what is written on the sheet. So hold on to that question just for a second. Okay? In this instance right here, what did we say about R? It's 0. So in this problem, we don't have to worry about R. It goes away. The W, the weight force, is labeled as how much? 1,000. We said earlier Bronco's mass is equal to what? 100. So if we have 1,000 newtons, oh, I didn't want to make that red. Right? If we have 1,000 newtons divided by 100 kilograms, what's the acceleration of Bronco going to be at that point? 10. Okay? Is that a coincidence? No. What's the only force acting on him at that point in time? Gravity. That's what gravity is. Just and what kind of acceleration does gravity here on Earth cause? Around 10, right? So at that moment, his acceleration is 10, okay? Because he's not moving, all right? Good at there. Good now? All right, so let's go to the next picture. All right. Sorry. What's going to happen to Bronco in this situation? What's going to happen to him as he's falling? He's going to accelerate. Physically, what are we going to see Bronco doing? Is he going to slow down? At this point, he's not moving, right? He's going to speed up. So he's going to go faster and faster and faster. But as he goes faster and faster and faster, right? What's going to start happening to him? He's going to start experiencing what? Air resistance. So a little bit later, now his free body diagram looks like this. Okay? We still analyze the situation the same way by using Newton's second law, and we still have to add those two forces to get the net force. Okay? But now let's talk about why it looks the way it looks on your sheet. Okay? We represent forces with arrows because they're vectors. If they're vectors, what do they have to tell us? Magnitude and direction. Both of them. Okay? So, here, if Bronco's falling straight downward, we still only have two directions, right? Up and down. And we can distinguish them by calling one positive and one negative. Now, in this case, your sheet has taken the liberty or decided on its own that this Bronco is falling downward. And he's always going to be falling downward. So they're going to call downward the positive direction, because he's always moving in that direction. Okay? And if downward is the positive direction, that means upward has to be the negative direction. Okay? Good so far? So that then means when we come over here to Newton's second law, we have W plus R, but those represent forces. Forces are vectors. They have direction. Which direction is W pointing? Positive, in the downward direction. Which way is R pointing? In the negative direction. So this equation now looks like this. Does that make sense? Okay? And if you're adding a negative number, that's the same as what? Subtracting, right? And that's why this on your sheet looks like that. Okay? I don't like the fact that they just jump straight to this. Kind of hope that you understand the whole positive negative thing, but that's how they get there. Okay? All right. So for our purposes now, right, in this situation, according to this free body diagram, what will be the net force acting on Bronco? Is it 600? Ah, it's positive 600, because it's which direction? In the downward or positive direction, right? This is 1,000. This is minus 400. So 1,000 plus a negative 400 is positive 600. Okay. Has his mass changed since he left the helicopter? Nope. That would be weird if it did, right? So that means now the acceleration of Bronco at this point is?
Positive 6. Hey, I said
It was. Okay. Oh, right way. Okay. It was. Okay. We didn't have that whole direction thing set out yet, so I just kind of, but it is. It's positive 10. Okay. All right. Now, so Jason, you asked before about what's the toughest thing on the quiz. Here's part of the toughest thing on the quiz. Okay? All right. So, let's interpret this answer. Okay? Bronco still has a positive acceleration at this point in time. Okay? He's moving in the positive direction, and the acceleration is in the positive direction. Physically, what is going to happen to Bronco in this spot? True. Is he going to accelerate? Yes. Okay. Now, the number on this picture is less than the number on this picture. Does that mean he's slowing down? Nope. He's what?
Accelerating less.
He's accelerating less. Is he speeding up?
His acceleration.
His acceleration is decreasing. But when you say slowing down, that implies that he's physically slowing down, but that's not the case. He's accelerating less. Is he still going faster? Yeah, there's a bigger force downward, pulling him downward, than there is resistance pushing him upward. He will still go faster. But will his speed increase as much as it was before? No. Okay? This won't be on the test, okay? But, because you asked before, right? It'll make sense in a second. Okay? If we had a velocity time graph going on, all right, it's going to look like this. Is the velocity of this object increasing the entire time that I've drawn it? Yeah. The y values keep getting bigger and bigger and bigger and bigger and bigger. But are they getting bigger as quickly as they were before? No. Hassan, go ahead. Okay. That's why I don't like us to use decelerate, okay? Generally speaking, when people refer to deceleration, they're talking about slowing down, okay? So he's not slowing down here, right? Joe, he's just what? He's accelerating less, okay? The example that, okay, if you're at a stoplight getting on the highway, the light turns green, the driver hits the gas. The speedometer on the car goes, right? Goes from like 0 to 30 in the first couple seconds. Down at the end of the ramp, the speedometer still goes up, but does it increase as much as it did at the beginning of the ramp? Not usually, right? At the very top of the ramp, the speedometer goes, like I said, goes up from like 0 to 30 in the first couple seconds. But down at the end of the ramp, it might only go from like 68 to 70 in a couple of seconds. Is that car still accelerating? Yes. Is its acceleration as big as it was before? No. Okay? It would still, both of those would still have a positive acceleration value, but the acceleration of the car at the top of the ramp is a large positive acceleration, but down at the bottom of the ramp, it's a small positive acceleration. But it's still positively accelerating. Okay? All right. So, physically, Bronco's going to go faster and faster and faster. Eventually, the fact that he's going faster is going to do what to his resistance force? Eventually, this is going to happen. Okay? Before we use that term, right, let's talk about it in terms of what we know. What's the net force on Bronco in this situation? 0. If there's 0 net force, there's 0 what? Acceleration. Is Bronco stopped here? No. Okay? So, hold on that second for just a second. Okay? Here, what is Bronco doing? Moving at a constant velocity. Okay? This is the highest velocity he will ever reach. How did the resistance force get so big? He continued to do what? Go what? That's the next picture. Hold on. He continued to go faster until the resistance force and the weight force were the same. Will he go any faster here? No. This is as fast as he's going to get. Aya, if we continued this graph, right, that would happen. Okay? This is constant velocity. That's supposed to be straight. It curves down a little bit. I apologize. It's supposed to be straight. Okay? So, Shane, tomorrow, we do it right now. What do we call this? This is terminal velocity. It's the highest velocity he will ever reach. If nothing else happens, he will continue falling at this velocity until he experiences another force. That force, right? Okay? That's no fun. It's no fun. Okay. All right, so we don't want, okay, and so Jason, building on our from before, this is where things can get kind of tricky as well, okay? So we don't want splat to happen, right? Well, Bronco doesn't want splat to happen. How's that, all right? So what does he do? Okay, he does this. All right, notice what has happened to the resistance force here. It's gotten bigger. Not because he went faster. He's running into more air now because of what? Surface area. He expanded, right? He didn't actually expand, but right, we're getting more surface area. That's more resistance. We still analyze this problem like this, and like this. Okay? Now, what is the net force acting on Bronco? Negative 200. Okay? Because this is positive 1,000, and this is negative 1,200. So the net force now is negative 200. Bronco's mass is still what? 100 kilograms. So now his acceleration is what? Negative 2. All right. What has started to happen now? Now he's slowing down. Okay? His velocity is still which direction? He's still moving which way? Downward. Hold on, wait. Let me finish this thought. He's still moving downward. He still has a positive velocity, but now his acceleration is upward. If we're moving one direction, but acceleration is in the other direction, physically, what are we going to do? No. He said go upward. No. His velocity is still which way? Down. That means he's moving downward, right? But something is pulling him in the other direction, right? Something is pulling him more up than down. If you're moving one way, but somebody pulls you the other way, physically, what are you going to do? You're going to slow down. Eventually, what might happen? Eventually, you might end up going the other direction, but right now, we're not there yet. Okay? So in this case, so Hassan, this we could classify as deceleration, because he's slowing down, right? Here, what's the net force in the next picture? Negative 1,000. Bronco's mass is still what? 100. So in this case, the acceleration is what? Negative 10 meters per second per second. Okay. So, here, we'll finish with this. We'll finish on this note, okay? At this point, right, if you watch a video of somebody skydiving, they pull their parachute, and this happens, right? right?
That's where I thought you were up.
What wants to keep moving?
Inertia.
Does their body want to keep moving? Yes. Do all the rest of their parts want to keep moving? Their parachute is attached to which part of their body? Your back, your waist, your chest, right? So that part slows down. But what do your arms and your legs and your head try to keep doing? Keep going forward, right? So that's why you do this. It's not really like you doing that, right? Whoa, hey. Can you at least wait? I'm not done. I'm still talking. No, I'm talking to all of you. No, I'm not done talking yet. So, good thing though you all packed up your stuff even though I wasn't done. Right? Right? That's inertia, right? All of your body parts have inertia. The parachute acts on your chest, so it slows your chest down, and all the rest of you try to keep going. It's the same thing with the seatbelts, right? In the car, you're trying to keep going. The seatbelt stops you here, but all the rest of you keep going forward.